Hi everyone, my name is Zheng, and today we're going to talk about post representations and coordinate transformations on the F110 system. We'll cover three things today. First of all, what are coordinate frames that we usually see, and what are the transformations that we see on autonomous vehicles, and why are they needed? And second, we'll look at the reference frames on our F110 vehicle and how to do rigid body transformations. And third, we'll go over TF and TF2 ROS, which are ROS specific frames and transformation packages that you can use in your code. So first of all, let's talk about frames and transformations on AV. And the big part of the question is, why do we need multiple frames? And why do we need to perform these transformations on an autonomous vehicle? And as we said before, usually on an autonomous vehicle, you can find multiple sensors on board. For example, LiDARs, radars, cameras, and sensors provide their measurement in the frame of reference specific to that sensor and that sensor only. So imagine having a LiDAR mounted on top of the vehicle. The measurement from the LiDAR gives us the distance from the obstacle to that LiDAR, but not the distance from the obstacle to the front bumper. But we probably want to know the distance between the obstacle and the front bumper, and in this case, frame transformations will come in handy. And same as a autonomous vehicle, we have multiple sensors on board our F110 vehicle, so the same transformation needs to be performed for better actuation and calculation to the environment around us. And the second reason that we need to do frame transformation on autonomous vehicle is that mapping is usually done by tying submaps together instead of creating a whole map all at once. So the animation shown is a demo of Google's cartographer in 2D. We'll be using it later in the course, and we'll talk about how to create maps from its SLAM algorithm later in the course. And for example, in cartographer, there are two subsystems. The local SLAM builds a succession of submaps. So as you can see here, each part inside the bounding box that I've shown is a submap on its own. And each submap is meant to be locally consistent, meaning that it has its own frame of reference and all the measurements are done in that submap's frame of reference. And the second part of the system is a global SLAM, which job is to find the loop closure constraints and tying the submaps together by using a global optimization. And its job is to create a consistent global solution. And as you can imagine, frame transformation comes in very handy here because you need to figure out the transformation between the reference frame of the different submaps in order to create a good global map. And next we'll talk about the reference frames that you can find on our F110 vehicle and why are there multiple of them. First of all, we need to know where the robot is in the world. So it'll make sense to have a frame representing the robot and a frame representing the world. So as you can see, for example, we use the laser frame on the car, and we use the map frame to represent the world. And we also need to know the relationship between the measurement frame and the actuation frame. So as you can imagine, on the F110 vehicle, you'll be measuring everything from the laser frame, and the actuation is actually done from the motor, which is a different part of the vehicle that's not exactly the laser frame. And as you can see, the measurement in laser frame and the map frame will be drastically different when you see it in different reference frames. So in this case, you can see some information about the environment and some information on the positional relationship between the robot and the world, but it is not absolute. Since you're keeping the robot frame static, you see the world rotate around us. But if you put everything in the map frame, the range measurement now makes sense. The observation matches up with the environment, and we can infer where the robot is. And for example, it's making a left turn here. And putting the two together, you can see sort of the difference between the two frames and what they look like. So in summary, why do we need transformation between frames? And to reiterate, first of all, the data is usually provided in the most convenient frame to the data source, i.e. the sensors here we have onboard our vehicles. And second, if we had two disconnected maps, for example, submaps in a SLAM algorithm, we might want to know their location with respect to each other within a global world frame. And third, once we have that map, we might want to localize ourselves on a map for a more advanced algorithm for navigation. And fourth, if an obstacle is detected in the laser frame, for example, maybe you want to know where it is in the world, for example, in the map frame, so it's easier to for a navigation task. And next, we also need to know the transformation between the frames of components on the car so that you can drive with higher accuracy. For example, if you're driving thinking that the motor is at the laser frame, you'll have full car lengths error in your actuation. And there are many more reasons if you can think about if you think about this more. And next, we'll go over the specific frames that we'll be using in our F1TENTH system. And for example, the three frames that we see in the picture here. So as a side note, in ROS, the frames that you see in visualizations usually have three axes, and the colors are corresponding to the order of RGB is corresponding to X, Y, and Z axis. So it's very easy to tell which one is the X axis and which one is a Y and which one is a Z. And for example, the frames that we'll be looking at here, the first one is map, representing the environment. And the second is base link, representing the actuation frame of the vehicle, and the laser frame, which is the measurement frame of the vehicle. So first of all, the map frame. The map frame origin can be set arbitrarily when you make the map. That means you just have to set an origin when you're first making the map and keep it consistent throughout your navigation task, and we'll be all good. And the map frame represents the environment around the robot. And then we'll have the base link frame. This is defined as the center of the car's rear axle. It moves with the car relative to the map frame. It is also where the car is actuated from. It can be used to represent the car's position since it's a frame fixed to the car because the car is a rigid body. And lastly, we have the laser frame, which is the frame the laser scan measurement is taken, and also moves with the car relative to the map frame. As we've talked about it before, the car itself is a rigid body, so we can assume that the transformation between laser and base link is static. And we also have something called the DOM. It's not exactly a frame. It is more of a history describing the relationship between the two frames, base link and map. As you can see in the simulation, it'll be more like a moving relative odometry frame. And next, we'll talk about how to actually perform frame transformations. So for example, if we take a look at our earlier lab, in the safety lab, when you defined only one TTC threshold for emergency braking, the distance between the wall and the car after the car is stopped is different depending on your traveling direction, since all the laser scan measurements are taken in the laser frame, which is not exactly where you might want to do this calculation from. And as we can see in the picture here, the laser frame is toward the front of the vehicle. And this could be remedied by adding a frame in the center of the chassis and calculate the TTC from there. So this will keep it consistent from going forward and backwards, where the distance between the front and the back of the car to that frame is consistent. All right, and next, how do we actually transform the measurements in the original frame into the new frame that we just added? So in order to do this, we'll have to first talk about some of the basic transformation terminology. So this will serve as a refresh for your robotics course, your Intro to Robotics course, where we extensively talks about frame transformations. So first of all, the first concept is the rotation matrix. So for example, in the figure here, we have a rotational transformation from frame 1 to frame 2 by counterclockwise by an angle theta. And we can write out the calculations as cosine and sines of theta in terms of the axes themselves. So as we can see here, we have the axis x2 is equal to cosine x1 plus cosine theta x1 plus sine theta y1. And then y2 is negative sine theta x1 plus cosine theta y1. And next, we can turn this into a matrix form. For example, x2, y2 equals r times x1, y1. And in this case, the cosine and sine terms all come together as a single matrix. And the r here is denoted as the transformation matrix. Oh, sorry, the r here is denoted as the rotation matrix, as you'll often see. And in this case, if you can see the pattern here is that the columns are actually the result of, for example, the x2 in terms of x1, and then the coefficients are written in the column of the rotation matrix. Next, what happens when we have a point in the transformation? So before we just talked about transforming the axis, but what if we need to represent a point that was defined in one axis, one reference frame in the other reference frame? So recall when we represented the basis vector of one frame as a linear combination of the other frame's basis vector. We can basically do the same here. So OP1 is the vector OP, so the vector between it's going from the origin to the point P in frame 1, and OP2 is a vector OP in frame 2. And as you can see, so the composition of the vector OP1 in frame 1 is px1 multiplied by x1 plus py1 y multiplied by the axis y1. So px1 and py1 are the two coefficients that we'll try to find and perform the transformation on, and the same goes for OP2. And next, we'll try to see how we actually relate the two together so that we can create a relationship or transformation between the two of them. So first of all, we take a look at the frame x2 and the point P prime here. So imagine if you keep the relationship between the point, the vector OP prime in the reference frame x2, y2, and you rotate the whole frame to the right. And we'll get something like this. So imagine that now x1 and x2 coincide with each other, and y1 and y2 coincide with each other, and you'll have a new vector OP prime, which is in the reference frame of x2, y2, but also in the reference frame x1, y1. And then instead of using two frames, we can represent these two vectors in the same basis vector now. So basically, OP, which is originally the vector OP in reference frame 1, it's going to be pxx1 plus pyy1. And the rotated OP vector, which is originally in reference frame 2, but we rotated it clockwise by angle theta, is now p naught x x1 plus p naught y y1. And all we need to do is to figure out the relationship between the coefficients, basically px and px, py, and p naught x and p naught y. And what is this matrix that's missing here? And we can see this will be exactly, we'll see later which matrix this will be, as we've seen before. But right now, let's denote the four elements as R11, R12, R21, and R22. And as it turns out, if you we're not going to go through the detailed calculations here, but if you go through the calculation, it will be the rotation matrix we derived earlier, which is the rotation matrix between the frame 1 and frame 2. So rotation matrix is one way to represent rotation. So in Ross standard, you also have quaternions. So for a good supplementary material, we recommend Lovell's virtual reality lectures. So this will be linked as a separate link in the slides. If you're interested in how quaternions work, that is a very good intro lecture. And we also have other representations like Euler angles and axis angle. We're not going to go into details here. So putting everything back together, we also add translation this time. So as you've seen before, we were only doing rotation, which means the origins of the two frames of reference coincide with each other, but now they don't anymore, and there is a vector 02, 01 between them. So what we do here is we can first apply the rotation, and then we apply the translation. And first we apply the rotation, right? We do the same thing. We rotate the reference frame 2 to get a p prime, and then we figure out the same way that we did before, where the p naught is going to be the transformation from frame 1 to frame 2, and the matrix multiplied by the vector p2. And then we apply the translation, which is basically we're moving the frame so that the two frames coincide with each other, and p naught is moved to the position of p1 as we see here. And it's exactly the rotation, rotated vector, and then plus the vector 021, which is the vector from 02 to 01. And as we see before, it's kind of very complicated to write out an addition here, and in fact we can represent this whole relationship, the transformation. Instead of doing two steps, we can introduce a new matrix H, which will represent the transformation as a whole that ties in both the rotation and translation. And again, if we write everything out, we'll have something like the H matrix we see here, which is the top left section of the matrix is the rotation matrix that we found before. We have a zero matrix at the bottom and a single number 1 at the bottom rightmost of the H matrix, and then we'll have the translation matrix on top right. This will represent the transformation that ties in both the rotation and translation. And we call these type of the transformation H's homogeneous transformations. It is a matrix representation of a rigid body transformation, as we've seen before. And for example, R here is a 2x2 if you're doing the transformation in 2D, and a 3x3 if you're doing it in 3D rotation matrix. And D, the vector D here is a 2x1, or again in 2D, or 3x1 in 3D displacement vector. And note that before we see that we have padded our vector point vector P2 with a 1 at the bottom. this is called the homogeneous representation of a vector. And it is 2 by 1 in 2D and 3 by 1. The display the point vector P is 2 by 1 in 2D and 3 by 1 in 3D, and the homogeneous representation of a vector will be 3 by 1 in 2D and 4 by 1 in 3D. And in our later vision lecture, we'll talk about why the homogeneous representation of a vector will come in handy, and why it is important to have such a notation. And again, coming back to our example, we're trying to do this basically transforming a measurement from the laser frame to this new center of chassis frame that we defined. And how do we do this in ROS? It might be the question that arises next. So we'll be looking at how to actually perform these transformations using ROS and the built-in packages that are available for you. So first of all, we'll talk about the ROS TF and TF2 packages, and what are their purposes, what are the available functions. So first of all, the goal of both of these packages is to maintain relationship between reference frames over time, and transform points or poses between two coordinates. As you can imagine, ROS is extensively used in robotics mainly because TF and TF2 is very handy at keeping track of all the reference frames that you might define on a robot with a complicated structure. For example, if you have a humanoid robot, you'll have tens, even sometimes up to hundreds of frames representing all the moving parts on the robot. The second purpose of these two packages is to broadcast this information across ROS, so that, as we talked about before, the nodes in ROS have subscriptions and publications. So in TF and TF2's cases, the publication is slightly different. It's more of a broadcasting behavior where it is broadcasting this information across ROS so that any node can subscribe to it. And it will be very useful for all of your future labs when we go to, for example, localization, and, for example, creating a navigation algorithm that utilizes localization. So highly recommended tutorials is actually the TF tutorials that ROS has provided us with. So first of all, you can look at the TF tutorials and the TF2 tutorials, and you can look at how, if you were using TF before, how do you migrate to TF2? So let's first talk about the ROS TF conventions. So if you, as we said before, for example, the rotation in ROS is usually quaternions. It's not the simpler to understand form of rotation matrices. So I would recommend everybody to go over the units, the orientation conventions, rotation representations, and even the covariance representations of this very specific rep that ROS created. They listed out all the conventions that they use. And they're also, this is less important, but there are also standard names for mobile base coordinate frames, which also has its own standard. So it will come in handy when you're trying to create your own TF system. So first of all, static transforms. So as we said before, our robot is a rigid body, which means the transformation between the frames that are on the robot are static. So it's used for frames for various hardware components, and it's usually defined by a robot description file or a URDF file. I've also provided a link to a tutorial here and see how those are created. You can also broadcast a static transform yourself from your code with either the TF package or the TF2 package. There exists a static transform between laser and baselink, for example, in the picture here. because as we said before, the robot we have is a rigid body, and the transformation between the frames we define on the car are static. So for example, let's take a closer look at a robot description file. This will be the racecar.exacro file in the F110 simulator package that you use for our simulation. So for example, we have defined a base to laser model, which is the static transformation between base link and the laser model frame. So as you can see, it is defined with zero relative rotation, since we're only having a translation in both x and y and z coordinates. So if you're interested in how these are defined, you can take a look at that file. It's pretty straightforward. And then the second way to create a static transform so that the whole system will know is to broadcast it through TF. You can either do it in a command line by running the static transform publisher node and give it the argument that it needs. So for example, the XYZ is the translation, and the QX, QY, QZ, QW are the rotation quaternions. You can also broadcast the static transform between the two frames in a launch file. So for example, you can just include the static transform publisher as a node that you launch alongside all your other nodes, and you also give the arguments for the node so that it knows how to the specifics of this static transform. So for example, let's say we want to add a frame or a static transform in our simulation vehicle. So but using command line tools, you can just run the static transformation publisher and then create a static transform with your given rotation and translation between the laser frame and your new frame. And another way is to use a launch file to include the static transform publisher node and then give it the corresponding arguments. And lastly, you can also do this by changing the robot description file. So this would be split into two parts. So first, you'll need to create the new frame and define the origin of the frame, and then you can create a static transform between this new frame to already defined frame with the translation or even rotation if you want to. Another concept that's in the TF package is a TF tree. So this, as you can imagine, the frames will all have relationship between each other, and even one frame will have like multiple, even sometimes multiple relationships between different frames. And TF tree in ROS gives us all the frames, their relative transformation, and it also keeps track of who is broadcasting each transform and how fast they're being broadcasted. So it's basically a tree that keeps track of everything. And if a frame is connected to the TF tree, so you can imagine if you add a new frame and you just connect it to the existing TF tree by creating a static transform to one of the nodes in the TF tree. And the nice thing about TF is that you can, once you do that, you can obtain all transformations between this frame and all the other frames that were also in the tree via TF. So it's very useful. And lastly, visualizing it is a great way to debug. So sometimes you'll have like frame related issues where the transformations are just not working. And to debug, you can as I've pointed out here, you can see the current TF tree and see if a frame is detached from the tree or it's the wrong node is is broadcasting the transform, or the transform itself is just wrong. So for example, this is the TF tree that we see in our simulator. As you can see, it keeps track of all the relationship between the frames. It also timestamps the latest published transform, how fast they're being published, and who's publishing them. There are also some other useful command line tools that you can use to display debug information on where TF is coming from, etc. So first of all, you can run the TF monitor node in the TF package. As you can see here, it's publishing very similar information that's displayed in the TF tree, but in a plain text form. You could also echo information to the TF information between two frames. So for example, if you're interested in the specific transformation between a source frame and a target frame, as you can see in the screenshot here, you can see the translation between the two, and you can also see the rotation in three different forms: in quaternion, in radian, in RPY radian, or in RPY degree. So it's the three conventions. And next, we'll talk about some of the TF APIs that are available to use programmatically. So we'll first talk about the relevant ROS messages. So as you've probably figured out by this lecture, since you've already done the ROS lab, the safety lab, you know that the ROS messages basically defines the information that's being passed around between topics, between nodes by topics. So we'll go over what are the relevant ROS messages when we need to use TF. Next, we'll go over the TF broadcasters and listeners. Note that the names here are different. Broadcasters and listeners are probably mostly used in TF, and in other ROS nodes, you usually see publisher and subscribers. And lastly, we'll go over what are the available functions for you that you can perform the coordinate transformation. So first of all, I need to clarify that the following information are in Python. There are also equivalent C++ APIs, so please check the ROS tutorial and documentation for specific ways to use these APIs. The names are roughly the same. So ROS has many messages for describing spatial information, and as you can imagine, it's crucial in doing frame transformations. If not all, most of them are within the geometry messages package, and they're useful for communicating spatial information between the nodes. It's often used even within other messages, for example, the odometry messages, which is essential for navigation. Some of them you can natively visualize in RViz. Most message types have stamped and unstamped variants, which means that some of them has a timestamp and some of them don't. For example, you have point versus point stamped, post versus post stamped. And as you can see in the screenshot on bottom right here, it is basically the struct of a post stamped message. So you'll have a header with a timestamp, a frame ID, and then underneath you'll have a post message, which consists of the position and the orientation, which is represented by a point message, and a quaternion message. The second relevant ROS message is the visualization messages. It's useful for visualizing the spatial information when you need to debug something in RViz. So for example, marker messages are very useful, and I've included a link to a tutorial here that goes over all types of marker messages that might be helpful for your specific project. So for example, the marker message is useful when you need to verify the correctness of your geometry messages. So for example, in the picture on the right here, all of these blue squares are actually post messages, and they have an orientation, they have a position, and you can visualize this in RViz to verify if you've done all your calculation or setting the transformation up correctly. Uh, and in the TF API, we have transform listeners. So the transform listener object can receive and cache transformation from broadcasters for querying. Some extremely useful methods that are available in the listener class are can transform, so which tells you if transformation exists between the target frame and the source frame at the time that you've specified. It can also check if a frame exists. It can also check the latest common time between a source frame and a target frame, which is the latest time where these two frames synced up and the transformation is available. You also have wait for transformation, wait for transform, which is given a time deadline. So note that the time here is a deadline for the method to run. And you can find the transformation between, so it will be blocking all your other code until a transformation is available between the target frame and the source frame. You can also use lookup transform. It's a similar method as wait for transform. Again, please read the documentation for a more detailed description of these methods. And next, we have the transform broadcaster. So this object can be used in a node to broadcast up-to-date transformation matrices or quaternions between frames. So for example, if you have two moving frames that you're calculating the transform by yourself and you want this information to be available to all the other nodes in your same ROS system, so you can use the send transform message to there are many different conventions on how this method could be used. And for example, here you can send transform as a translation vector, a rotation matrix, and the two child and parent frame that's that the transform is relating to. Again, please read the documentation if you think this will be useful in your code. And for an example, you can check our simulator source code. This is used extensively in our simulator. And next we can talk about how you will perform a coordinate transformation that is transforming a point or a pose that's defined in one frame and put it into with the other frame. So in ROS, a tf.tf transform listener object can also be used to transform some of the geometry messages types. For example, you have the method transform point, which is transforming a point from a target frame to from your original frame that the point is stamped in to a target frame. And you have the same thing for transforming a pose. So you don't have to do any math yourself, and TF, for example, the TF package will take care of everything. Note that a very important point is that the point pose messages used by these methods must be stamped in the header by the source frame using the frame IDs field. So if you don't have that, then TF doesn't have any information on what the point is currently in or what frame the point is currently in, so it's going to throw an error. ROS also provides some handy helper functions for transformations. For example, in this tf.transformations package or module, you have things like converting a quaternion to an RPY convention, or you have an RPY convention, you're trying to find the corresponding quaternion. Again, I recommend going through the file. There's a lot of handy utility functions that you can use if you try to do the transformations yourself. Yeah, again, read the documentation. There's a lot more detailed descriptions on what all these methods do. Okay, so let's go back to transforming a measurement in our example. So for remember that laser scan messages are in polar coordinates instead of Cartesian coordinates. So it's you need to have one more step before you can perform the transformation. So first of all, you can put the measurements into a data type that TF could understood. For example, point stamped, point cloud, post stamped, vector 3, etc. Know that the TF2 supports more data types, even eigenmatrices. So if you're interested in using eigenmatrices, this is specific to C++. By the way, if you're interested in using eigenmatrices, I recommend everybody to read the documentation for TF2. There are even more data types that you can transform. And then you want to make sure the transformation between the frames that you want exist using TF. So for example, the TF tree we've mentioned before, so you want to make sure the new frame you added is in the tree. And lastly, once you've put the measurement into data type that TF could understood, you can transform the measurement to the new frame with TF using the methods that we mentioned before. So, what have we learned so far? As a reminder, coordinate frames and transformations, why do we need them? The biggest part that we see on an F110th vehicle is that your measurements are all taken in the frame of reference of the sensor, and your actuation is from another frame. So for accuracy of our actuations and for the accuracy of, for example, obstacle detection, we want to have the transformation information between the frames so it's easier for us. We also talked about reference frames on the F110 vehicles, for example, the base link frame, the laser frame, and we also talk about the rigid body transformation. So the homogeneous transformation that we talked about, how do you put everything together with rotation and translation. And lastly, we talk about how to actually do these transformations in TF or TF2. So in lab 3 and 4, you'll be doing reactive methods. These are all planning in local frames. So there's less to worry about actually performing these frame transformations. And after lab 4, we'll move on to map-based methods. And the TF and TF2 transforms will be very important since we need to perform planning in a global frame, so that your measurement needs to be transformed around to get a better idea of the environment. And thanks for listening. That's our lecture on post representation and transformations in F110. Thank you.